Rivers Conservation Trust. And thank you all for joining us. I'd like to introduce Kathleen Thornton. She's a research specialist at the Darling Marine Center in Walpole and works very closely with us on this analysis because she is our guru. We are so fortunate to have this partnership with the University of Maine Darling Marine Center and specifically with Kathleen and a few of her colleagues as well, because they lend their talents and our capacity is greatly enhanced in terms of the data quality control, in terms of what we can offer volunteers, in terms of the information we can get out of the data afterwards and our ability to interpret it. So Kathleen, thank you very much for always being a part of this, and thank you too to your colleagues who are part of this as well.
It's been a pleasure working with you, Sarah. And I'll just pop in to say that citizen scientists are doing really important work monitoring water quality in Maine. We're very fortunate to have such dedicated organizations and volunteers. And it's a privilege to work with you all.
Fabulous. All right, so let's go to this next slide and kind of set the stage for where we are. We are along the edge of the Gulf of Maine, and the currents that we might be largely unaware of that are circulating in the Gulf of Maine travel in this counterclockwise position, just as this image on the left-hand side shows. And it also shows you a little bit about why the water is so cold. You know, it comes from the deep Atlantic in some cases, and or in all cases, and it travels northward, and the cold water is brought along the coast, and it's high in nutrients and highly productive, and it gets pulled in and out of our estuaries, and all the nutrients that are on the landscape have, can enter the waterways and feed the animals and plants that are growing there. So it's an amazing place, and I know probably a lot of the reason why many of you are here is because you already love this place and you're already very devoted to it. So this is just another opportunity for us to understand it better and to be good stewards of it. This other image about the estuary morphology here is just a way of illustrating a little bit in brief that the estuaries along the coast of Maine are all substantially different. And anyone who's been out on the water or driven up and down or even visited different sites along these estuaries is really probably very well aware. And a lot of the difference comes from the water that comes in from the Gulf of Maine. And when you think about the, if you were to drain the Gulf here a little bit, like a bathtub, and then look at the estuary and kind of the shape of the basin where the water goes in and out. You can compare, for example, in this image, you can look at the Sheepscot here, which has this very relatively uninterrupted channel with relatively few islands. Can you all see my cursor? I'm moving my cursor up and down here, so it makes sense. Okay, good. So, there's a relatively uninterrupted chain or gully here. Where the water can go up into the Sheepscot, and it's not interrupted by islands. But if you were to look at some of these other areas, Damariscotta, the Madomic, you've got islands and even hills and mountains underneath the ocean here, underneath the water, and so that's interrupting and causing in some cases warming. And in some cases, just a different type of flow into the estuary itself. So the estuary itself, when I talk about what an estuary is, it's this area of water where you have fresh water flowing off the landscape, and it's mixing with the salt water that's flowing from the Gulf of Maine. And so wherever you have that fresh water and salt water mixing, you have an estuary. And our estuaries are there's certainly similarities, there's certainly some commonalities, but they all have their own personality. And if you're a sailor or kayaker or anything like that, or a fisherman, you're very well aware of those characteristics just by nature of being out there. And the Damariscotta estuary in particular has a really diverse group of habitats. And because of that, it has a really high concentration of wildlife. And a number of years ago, now this is relatively old information, but 20% of 161 species of significance were identified in the Damariscotta estuary, and specifically in the Great Salt Bay, the upper part of the estuary. As being 161 species of significance to the Gulf of Maine, and they occur in this watershed. And a lot of that is because of these habitats that we have, and there's a short list of them here, and that's not even all of them, but because of those variety of habitats, we have a wide, diverse wildlife population here. And some of them are really relatively unique or not commonly seen in other areas, like horseshoe crabs, for example, are certainly horseshoe crabs are found along the East Coast, but they're not found everywhere along the East Coast. And our population may be a relic, somewhat isolated population. The furthest east they go is to Taunton Bay. And so it is a special place. And the image here above the habitat list is an image of some eelgrass beds under the water. And Kathleen later is going to talk about eelgrass beds in particular. They provide a habitat that is essential for a lot of wildlife, and the eelgrass provides a lot of important functions in terms of containing sediment and protecting wildlife and being a nursery ground for fish and other creatures. So very important habitat that we'll talk about later. And of course, the Damariscotta is worldwide. It's known for oysters. And just a call out to the farmers who are growing oysters, and for all of us who enjoy not just oysters, but seafood in general, and just to note the strong tie of the estuary to our local economy. One direct way is through oysters, but there are many other ways through tourism, and kayak businesses and fishing businesses and so forth, that this estuary supports a lot of elements of our economy locally. So what are the things that we are concerned about? What are we worrying about, and why would we go through all this effort to monitor this estuary? And obviously you're here, and so you must be aware that there are potential threats out there in the world. And we're not worried, of course, about large factories at this point. We don't have that kind of point source pollution. But what kind of pollution might we see, and what are we on the lookout for? Well, every time you have any activity on the landscape, you have the potential for sediment, little bits of dirt, to get washed off by rains into the water. And with that can be carried anything that's on the landscape. Some of that can be, nutrients that are important for phytoplankton blooms. Some of that can also be too much nutrient material, so that you are impacting the water negatively over time. You can have too much of a good thing. And so I won't go into all the possible sources of pollution, but many of us are aware of, cars and our activities on the ground, for example, putting down fertilizers or pesticides or herbicides, and the potential impact for all of that. And then there are global issues like coastal acidification, where we have the impacts of the water coming in from the Gulf of Maine tied to the pollution sources that may come off the landscape locally. And these larger issues like coastal acidification can be impacted and are closely tied to the nutrients and dissolved oxygen and temperatures that we see locally. So what do we monitor? And I'll do a special call out right now to our volunteers, and we'll talk more about our volunteers in a moment, who are amazing, wonderful people. We monitor dissolved oxygen and temperature and salinity and transparency and pH. That's more recent for us, and total nitrogen. And we use a unit that's essentially like this one here. This is an image of a sonde, where it's basically a computer with a screen, and it's got a probe that we lower via a long cable. And that cable allows us to be able to measure temperature and dissolved oxygen and salinity and pH at depth. So we can measure, down on the bottom and up at the top and everything in between, which is a really amazing tool for us to be able to use. We use a Seki Disc. Like, this is a picture of Tam Green, and she's using a Seki Disc here. It's a very, it's sort of the other end of the spectrum. You can use something that is more of a recent acquisition for us. And then the Seki Disc, I think, was invented by an Italian scientist in like 1620 or something like that. And it's just a black and white disc that we lower, and what we do is we kind of calibrate our us against each other to make sure that we are all doing it in the same fashion. But we want to lower that disc until we can't see it anymore, and then pull it up just slightly so that we can just barely make out the black and the white. And what that's telling us is something about that there's stuff in the water, and it doesn't tell us what's in the water. So we don't know, if whatever's blocking our view of that black and white disc could be sediment. It could be phytoplankton that are feeding bivalves. It could be any number of types of pollution that could get into the water, and it could be something natural and appropriate. Sometimes the water can be colored from tannins in some areas, from the rotting material of trees and so forth. So all these tools tell us quite a lot, but they don't necessarily, this is all information that we use as indicators. That is to say, they don't tell us exactly what the pollution source is or where it's coming from. This is information that then we use to do further detective work. We also take samples of the water, and these are analyzed by Kathleen at the lab at the Darling Marine Center for Total Nitrogen. And so it's amazing that really that we have a lab that we can work with that has all the quality controls and capacity that it does. And Kathleen sometimes is able to integrate that work with her students as well. So we love that we are able to provide information the students can and experiences her students can work with. So and then where do we do this? Where do we take these measurements? This map actually doesn't have the sites on it, and you'll get a little bit more familiar with some of those sites in a few moments with another map. But I'll just point out that here's Great Salt Bay up here, and here's the estuary, and then here's the bridge in town. And then we have a couple of sites, one in town, one right off the dock in town, and then we have I'm sorry, I should back up. We have a site right at the base of Great Salt Bay here, off of a person's dock here. And then we have a couple sites right in the harbor. And then we have several sites out as far as the Darling Marine Center, and which is in Walpole. Our sites are located in the middle of the river, so they're accessed by boats, with the exception of the one up in the Great Salt Bay area, and the one that's right on the dock. We can access the one that's right off the dock there. And so they're accessed by boat. So sometimes folks are using our boat, the Coastal Rivers boat, and sometimes this year in particular, we leaned heavily. In fact, we relied entirely upon Dick and Emily Mackenzie and their boat. And so we'll talk about that more in a moment. But in a normal year, our volunteers go out on the Coastal Rivers boat, and we have volunteer boat captains, and they take people out and do the work as a little team. Somebody is a scribe, somebody takes samples, and somebody works with the sonde, and somebody drives the boat. But this year, because of COVID, we had to really revamp what we were doing. And err on the side of being as careful as possible. And what we landed on was asking Dick and Emily McKenzie, who fortunately said yes, to do all of the monitoring for us. And I think well, I know that they engaged some of their family members as well, but at any rate, and their boat. And so that was an amazing score for us, and really important. So, it's the gathering water quality data it's one of these things where it would really be a shame for us to miss a year. I mean, once that water is gone, it's gone. And so we wouldn't have an opportunity to get that information ever again. And sometimes that sort of situation can help to fill in gaps in our understanding of what's going on out there over time. So it was really, really wonderful that Dick and Emily are able to do that with us, for us. And here's some pictures of people having fun doing the monitoring, just so you get a sense of what it looks like. This is Larry Mayer doing a training with our volunteers, explaining how to take total nitrogen samples, and Gisela and Tam working on the boat, and Bob Barkalow, who is here this evening, taking a nitrogen sample, which he looks appropriately pleased about. And all of us, we also belong to a larger alliance of organizations up and down the coast, from Belfast to Casco Bay, and it's called the Maine Coastal Observing Alliance. And we do things like calibrate our instruments so that we know that our instruments are all working in the same fashion, so that if we want to compare data, and we do want to compare data, when we compare data, we know that that information is valid and useful across one estuary to another. And so these folks are from different organizations in our area, and they are working with us to make sure that all of our instruments work together, and we can talk to each other. And this has actually been an amazing development that was initiated in 2013. MCOA, we call it, the Maine Coastal Observing Alliance, to be able to compare data and understand from one estuary to another a little bit about what's going on. And Kathleen will talk more about that, I believe, as well. And in fact, that's my cue for Kathleen to take over and explain some of the more science and go through the analysis she's been able to undertake recently to look at some of the data that's been gathered.
Okay, I will share my screen.
I guess I will just check and before we go and have you jump into that. Are there any questions, Hannah, that I should attend to before Kathleen jumps in there?
Nope, we're good so far.
Excellent. Okay, go ahead.
Okay, yes. Great. Well, thank you, Sarah. That was a great introduction. And as soon as our COVID restrictions are lifted, we will be having be open for citizen scientists to come to the lab to do the cross calibrations. I really miss having you all there to do that. So I'm going to talk a little bit more about some of the things that Sarah mentioned as far as nutrient input and how that excess nutrient input and how that affects the estuary. Most of our estuaries and coastal waters in Maine are nitrogen limited, which just means that the phytoplankton in the water pretty much have everything else they need to grow. They're just waiting for nitrogen. So when we put nitrogen into the water, either through fertilizer or sewage or dog poop or any number of things that can put nitrogen into the water, the phytoplankton are really geared to grab that, particularly inorganic nitrogen, which would be nitrate or ammonium. So as soon as that nitrogen hits the water, they start growing. And because phytoplankton are kind of the algae, phytoplankton are like plants, they need light, so they tend to grow up in the water column where there's lots of light. And as they grow, they're a lot like terrestrial plants in that they take up CO2 and give off oxygen. And that's all happening in the upper parts of the estuary, the upper part waters of the estuary. I should say the top of the water column. And that's fine. That's great. But the problem arises when those phytoplankton, which have taken the dissolved nutrients and turned them into particles, their cells, when they die, they can fall to the bottom because they're particulate, that all of those nutrients they took up are in their cells and they fall to the bottom. And these blooms tend to grow. When they get excess nitrogen, they grow exponentially really fast, and then they die. It's a bust and boom kind of thing a lot of times. So they fall to the bottom. When they fall to the bottom, they slowly rot. And you can think of rot as being the opposite of photosynthesis, in that when organic material rots, it takes up oxygen and gives off CO2. And there's also a pH effect too. When these cells are growing and photosynthesizing, they're taking CO2 out of the water. And because CO2 dissolved in the water increases the acidity of the water or decreases the pH, and that's pH is an inverse scale. So when acidity goes up, pH goes down. They increase the pH of the surface waters, but then the rot decreases because it's the opposite process, decreases the pH near the bottom. And when in certain situations, for instance, if you look at the graphic on the right and the left hand, I guess the top left block, this is an instance where you have a lot of fresh water coming into a river from the right. It's labeled salt wedge. So when fresh water comes into an estuary, the tidal water kind of comes in and out, but because that fresh water is lighter, it kind of sits on the top. And that's one way you can set up this layering or stratification. And when that happens, sometimes all that rotten stuff gets trapped at the bottom, and the tide comes in and out, and it just kind of sloshes back and forth, but it doesn't ever go away. And this can cause problems because most of the critters that we harvest are on the bottom, shellfish, finfish, and just from an ecological standpoint, it can be really bad. And I don't know, some of you have probably lived here for a long time, like I have, and can remember back when we used to have fish die-offs, and before the Clean Water Act, the waters in Maine were not clean, and a lot of times there was so much of this rot going on that fish were dying when they were on the bottom and washing up on shore. Thankfully, we don't see that very much anymore, and we're trying to avoid that. But that's one of the reasons these monitoring programs are so important, is because a lot of these places have not been, there's no baseline monitoring for a lot of our estuaries and coastal waters. And when you try to find something, all you can find is back before the Clean Water Act, when it's really not relevant to what we're doing now. Dissolved oxygen. I wanted to say a little bit more about dissolved oxygen. There are various ways that we report measurements of dissolved oxygen. One is just a straight concentration, milligrams per liter. But another concept that I'd like everyone to understand, because it adds a lot of meaning to the data as I talk about it, is a percent saturation, oxygen saturation. And it sounds complicated, but it's really not. So if, as an example, if I were to take a glass of water and put it on a counter and it had nothing living in it, no algae, no bacteria, it would come to equilibrium with the atmosphere. And the oxygen in the atmosphere would dissolve into the water, and it would just stop. If everything was static, at some point, the level of oxygen in the water would be at equilibrium and it wouldn't change. And that's what we call a saturation concentration. And there are things that affect that, like temperature, pressure, and salinity can all affect the concentration where oxygen is at equilibrium. So for every combination of temperature, salinity, and pressure, there's a level of oxygen in that water that would be there if it was just sitting in the air. because it comes to equilibrium. And we call that the 100% saturation level. And that can be calculated if you take into account those three things: temperature, salinity, and pressure. If you measure 8 milligrams per liter of oxygen in a water sample, unless you're much more intelligent than I am and better able to do calculations in your head, you really don't know where that is compared to saturation. So a lot of our instruments will report it both ways. And what the reason that's useful is if we have a reading in the estuary that's 100% saturation, we know that, there isn't a lot going on. It's just at equilibrium with the atmosphere. But if the dissolved oxygen concentration is 120%, 140% of saturation, then we know something's going on. And most likely that means there's phytoplankton growing in that water and adding oxygen to the water. You can also get an increase over the saturation level if you have a lot of turbulence, waves, rapids in a river, that kind of thing. But in the estuary, a lot of times it's phytoplankton growth. And the opposite is also true. If we're below that, then we know that the level of oxygen in the water is less than it would be at equilibrium. So something's taking the oxygen out of the water. And that's usually this rot, or another way to term is respiration. So it's a really useful number. And you'll be seeing it as I go through the rest of the slides. So in a shout out to the Mackenzies, I'm really pleased that they were able to get us some 2020 data. And the graphics I'm using today, I am keeping pretty simple because these are things that if you have Excel, you can actually do yourself. So these first graphs show depth on the y-axis. So if you look in the left-hand graph at the top of the y-axis, it's 0 and it goes down to 12. Those are meters, not feet, meters. And across the top is temperature in degrees centigrade. So what we're doing now is we've made this little graph in Excel that basically allows us to look sideways into the water column. And this is station 7. And these are data that were collected this year. And each line represents a different date. And you can see that as we go down through the water column from 0 to 12 meters, the temperature is decreasing, which is what we would expect. But if you have access to a data set like this, and you're curious and you want to see what the water column looks like, this is a really easy way to just do this in Excel. And you can get an idea of how this site is behaving over the course of the year. And can you see my cursor? Yeah, okay. So this bluish green line is July 6th. And then over here is the end of July and August. And then in September, we come back over here. So the temperature starts colder, gets warm. So we start to see maybe a little bit of that stratification I talked about. And then in September, we're getting back to those temperatures. And over here, it's the same site. And these are taken with that sonde that Sarah talked about, where it's lowered down into the water and it's taking readings as it goes down through the water column. And we come back and we download the data and we get this profile, we call it, looking into the side of the estuary. And this is the same station, only it's pH. So really useful data, and we're really glad we have 2020 data. And that's just a little example of how you can look at the data yourself if you have access to these profiles. So this is kind of a complicated graph, but I don't want you to have to figure out what all this is really, but what I want to look at is the bigger picture. So this is a graph of the total nitrogen. And like I said, and Sarah said, nitrogen's coming from the landscape, and it can cause problems and lead to dissolved oxygen depletion if we have too much Suddenly I can't see everyone. There we go. There we go. If there's too much nitrogen, so total nitrogen is a really good kind of bellwether measurement because it takes in all the forms of nitrogen, but it usually correlates with bacterial contamination and that sort of thing. And if we see high total nitrogen consistently, we can then go in and try to figure out where it's coming from and what form it's in. So we do total nitrogen analysis at the lab. This is just a graph of all of the total nitrogen data that have been taken from the coastal river sites. These only include at this point the samples taken by coastal rivers. There's some collaboration that was done with MCOA, but there isn't much of that data in here at this point. But we're starting on the left of the x-axis with 2013, which was the first year that we collected these data. So as you go across, it's 2014, 15, 16, 17, 18. And I apologize for not labeling that on the x-axis, but we're going from 2013 to 2020. But really what I want you to see overall is that these nitrogen levels are pretty low. And this blue line represents 0.32 milligrams per liter of total nitrogen. And that's the point where you can start to see harmful effects with eelgrass if the total nitrogen gets higher than that. And that's because of the competing algae. They block the light so the eelgrass can't get the light it needs because it's stuck on the bottom and the algae are growing over it and shading the eelgrass. And then they can also actually grow on the eelgrass and fall. That rotting stuff can fall on the eelgrass. So when you get nitrogen above 0.32 milligrams per liter, you start to have negative effects on eelgrass. So looking at the graph, there are quite a few points that are above 0.32. And the stations are here. So station 1 is in Great Salt Bay, station 2 and 3 right in town. Station 7 is at the Darling Center, and the others are in between in sequence. You can think about it that way. So most of these occurrences of TN above 0.32 are either at station 1, station 2, station 3. There's a few scattered ones in the middle of the estuary, which is what I would call, station 6 and 7, but for the most part in the upper estuary. The red line is 0.45 milligrams per liter of nitrogen, which is when we really start to worry about other things being affected. And that's a level where we need to really take some action to clean things up. And we have a few points at station 1, 2, and 3 that actually were above that at various times. 2014, 2013 were very rainy, wet years, and we had a lot of runoff. Well, I'll talk about that a little more later. But the main message I want you to get from this is the vast majority of our samples are low in total nitrogen, which is a great thing. Now, we're going to spend a lot of time talking about the places where that's not true, but I wanted to show you there are a lot of places that are doing great. The other thing we're going to look at is dissolved oxygen. And because we only take dissolved nitrogen measurements at the surface, I was able to put them all on one graph, but the dissolved oxygen is measured with the sun, so we have profiles. So it's a little bit messier. So I've broken it down into 3 graphs. The first graph has station 1 and 2, the second station 3 and 4, and the third graph has station 5, 6, and 7. And those lines that you see across are similar to what I did with the total nitrogen levels. That's a saturation of 70% of 100% saturation. So we're at 70% instead of 100. So we're below that equilibrium level by 30 percentage points. And that's when you start to see effects on the animals that live in the water. Again, though, you can see that the vast majority of our samples in the Damariscotta estuary are above that. We rarely see these low oxygen levels that used to be so common years ago. And we can thank a lot of things for that, but in large part, it's the Clean Water Act. But where we do see these depleted levels, we want to take a closer look and maybe try to figure out why. And so again, we're going to concentrate on the problem areas, but I do want to emphasize that by and large, the oxygen levels in the estuary are very good. So this little matrix shows us where and when the dissolved oxygen levels were below that 70% level, with the dates in the first column and the station numbers across the top. So station 1 is in Great Salt Bay, 2 and 3 are right in town, 7 is at the Darling Marine Center, and 4, 5, and 6 are in between. So the mid estuary stations, most of the below 70% dissolved oxygen readings were in the deeper water, which could mean that there was some sort of stratification set up at that time in September and October, but we need to do some pretty deep analysis of the data to do that, but that is noteworthy that almost all of those low DO levels in the mid estuary were at depth. At station 1 and 2, station 1 hasn't been actually, there have been some years we haven't gotten to station 1, and it hasn't been sampled as much as the other stations. So we don't want to read too much into those 3, but we did have some low readings in Great Salt Bay. But station 2, obviously, that's at the town landing. Obviously, something's going on at station 2 with dissolved oxygen. It's consistently low. And on 628, we saw low dissolved oxygen across the board. I tend perhaps not to believe that just because every single station had low oxygen. So my guess would be we would exclude that from our final data report, and there may have been an issue with an instrument on that day. And this is just sort of a different way of saying the same thing that we just said, but this shows of the times that dissolved oxygen was below 70%, what time of the year was it? So June and July, the instances of low dissolved oxygen were higher. So if we're going to try to zero in on station 2, that may be the time of year to do some extra sampling. And this is just the same graphic in the upper left. Again, singling out station 2. So if we look at Seki depth, which Sarah showed you was the disc that shows water transparency, there are a few things that can affect that. One is particles in the water, phytoplankton, sediment. The other is dissolved organic material, kind of like you'd see in a bog, that tea-colored water. Both of those together can affect the Seki depth. So I graphed dissolved oxygen saturation level with against Seki depth. And if we see a straight, a linear relationship, that means that they're correlated. And it does seem that at station 2, there is a relationship between Seki depth and dissolved oxygen. And that's great, because if we're measuring Seki depth, then we can characterize a site and say, dissolved oxygen levels correlate with Seki depth. Then we can go out and take Seki depth measurements. If we can't afford to go out with our dissolved oxygen sensor, we can at least do Seki depth and learn something about dissolved oxygen from that. There seems to be some, although it's not very tight, relationship between dissolved oxygen and salinity as well. But that's not as tight of a relationship, and we have some outliers there. So these are the kind of things that we can either do with our statistics programs like R, or we can just look at these simple graphs and see if we can try to figure out a relationship. And we have our students do that. We have them just do these simple graphs to see if there's a relationship between two parameters. If there's a positive relationship with salinity, then that tells us something about whether a pollutant is coming from freshwater or seawater. And with dissolved oxygen, in this case, it's not all that clear, but in some cases it is. And this is just a map. This is the bridge between Newcastle and Damariscotta, and the town landing is right here, and station 2 is right in here, and station 3 is out here. So they're both very close to town. Now we're looking at total nitrogen. And these are the stations and the dates where we had total nitrogen above that 0.32 milligram per liter level, where eelgrass would have a hard time growing. And I haven't found any indication that there is eelgrass right in town. That may be because it was there once, but because we're above 0.32 milligrams per liter of nitrogen, it's not there anymore. But it also could be it just was not an area where eelgrass was growing. But regardless, we don't want to see these consistently high total nitrogen levels. And station 4, 5, and 6, 7, they rarely have high nitrogen. So if we want to hone in on where the nitrogen might be coming into the estuary, we really want to look at station 2 and 3. And I'll just say also that other measurements that we've done for other research projects have shown pretty consistently that the freshwater coming in to the Damariscotta estuary into Great Salt Bay is not as high in nitrogen as what we measure at the Midden site and in town. So we feel that the nitrogen is coming in somewhere in the town area, and because it kind of sloshes back and forth. In the Damariscotta estuary, the upper part of the estuary, where station 1, 2, 3, and 4, I believe, it has a very long residence time, meaning that when the water comes in, it takes a long time before that body of water goes out. And that's because Glidden Ledge, which is down river, down estuary, is kind of a barrier to passage of water. It's a narrower channel for water to go through. And then you have a basin above that. So it's like a big incubator almost. And it takes 28 days that the water sits there. So there's a lot of time for biological things, phytoplankton to grow and that sort of thing. But if we introduce excess nutrients into the upper part of the estuary, they're going to be there for a while. So again, this is a different way of looking at the same data. Look, and this shows that by and large, July is the time when we have high nitrogen readings. So if we really want to look at what's happening in town, why we have these high nitrogen levels, sometimes we would probably want to do that additional work in July. This is total rainfall. It's from the Wiscasset Airport, which I found is the most consistent over the years that we have sampled. So it's not totally in sync with the Damariscotta estuary, but a lot of the rainfall recording stations are missing data, but this is a complete data set. So 2013-14 were very rainy. And then we had kind of a lower rainfall. This is just May to October. And then the levels kind of came back again. I'm really surprised at 2020 because I thought it was, a desert at my house, but evidently not. And then on the right side is the rainfall by month, and these are the averages for the years that coastal rivers has been sampling the estuary. So June is the high rainfall month, and then September. So if we're looking for runoff, again, the effects of runoff, those would be good times to go out there. So coastal rivers has only been measuring pH. You started in 2018, I believe, and we've only had one point with a pH below 7.8, which is kind of an indicator. Ocean water has the salts in the seawater act as a buffer. So if we see pH getting below 7.8, then we want to kind of look and see what's going on. And because we only have 3 years of data on pH, we've only got one point, which I wrote it down here. It was August 13th, 2018 at Site 2, right in town, was the only time we recorded a pH below 7.8, which is great. This is a map of the Maine Coastal Observing Alliance stations, MCOA, and this shows all of the times that any of these stations showed a pH of below 7.8. The black station markers mean that those stations have never had a pH below 7.8. And the symbols are graduated based on the percentage of times that we went out compared to the total sampling days at that station, the percentage of times that we went out and found a pH below 7.8. And Belfast we only have 1 year's worth of data, so I wouldn't put too much stock in that right now. That's just from 1 year. But the other stations we've sampled over multiple years. So there are quite a few stations, some obviously more than others. And I meant to label all of these, but if you can see my cursor, I'll just explain. This is Belfast, Rockport Harbor. This is the West Keg River coming out of the West Keg Marsh, which is a great birding area, a very productive salt marsh. This is the St. George River, the Madomic River, my hometown, Waldoboro. This is the Damariscotta River, the Sheepscot River. We have sites in Booth Bay and the Kennebec and down in the Freeport at the Harrisicot. So there's quite a lot of instances of low pH. Now, I said a few slides ago that we had a lot of rainfall in 2013 and 14. And MCOA started sampling in 2014, and were not able to sample pH in 2020 because of the COVID pandemic, but they did it through 2019. And this is a sort of the entirety of their data for the time that they were measuring pH. And in 2014, we saw this anomaly where we had, at the end of the year, this cold, salty, deep ocean water coming up into the channels of the estuaries. And we've had lots of theories as to why that happened and why it happened when it did. It may have something to do with that higher freshwater input. And you remember that slide with the salt wedge setting up that stratification or layering could have had something to do with it, but we just don't really know. But a lot of these instances of low pH were in 2014 and at the mouths of the estuaries. So here I've removed those. So I've taken out all of the data from that anomalous year of 2014. And these are not great size graded symbols. They're just symbols of where we have found pH below 7.8 outside of the year of 2014. So it would be 2015, 16, 17, 18, 19. And the Damariscotta only has one station I believe it's station 2. The icon, so the symbol's so big, but it's either station 2 or 3. Again, that's great. But if you look at some of the other estuaries, the Medomic in particular, and I don't know if any of you have been following the news. There's been they've been trying really hard, the Medomic project, to clean up the Medomic estuary. It's the most productive softshell clam estuary in the state. And they've been having consistent problems with bacterial contamination. And they've been doing a great job tracking that down, sleuthing it out. And it's a great collaborative project. But we also see, I don't have a slide for that, but we also see higher nitrogen levels there as well. And like I said, bacterial contamination and the total nitrogen tend to correlate. And also this low pH. And in Booth Bay, we see, this is Booth Bay down here. There's some in the Sheepscot, and in the Kennebec, there's also low pH, but the Kennebec carries so much fresh water. A lot of the low pH we see in the Kennebec is due to that massive amount of fresh water coming into the Kennebec. It looks similar in size to the other estuaries, but it carries way more water than any of these other estuaries by order or two of magnitude. And the Harrisegit is very close to Freeport. So this is a great baseline, right? And I was just thinking this morning as I was talking about the MCOA data on a presentation, a lot of these estuaries, when we started working in them, there was no baseline water quality data, nothing. And the only data we can find is from what we did find from the 70s, and it's just so irrelevant now because the systems have changed so much. But this citizen science work is so important because if we can't track climate change, if we don't have a baseline, right? Once you have a problem and start sampling, it's too late because you don't know what it was. And systems are always changing, and I feel like it's always better to start now. Start now, even though, it's never too late to start. And so what Coastal Rivers is doing in the Damariscotta is fantastic. And it's just fantastic that we have so many years of data. So these data provide a baseline so we can see any changes that occur. At the same time, they point out very clearly where there are areas that we need to work on. And one of the great things about these types of problems, like I don't want to say there's a great thing about a problem, that doesn't seem right. But when we think about ocean acidification, a lot of times we're talking about CO2 levels in the atmosphere and the CO2 going into the water. And sometimes it's hard to feel like you're making a big difference. But in coastal acidification and coastal nutrient overloading, there are a lot of things that we can do. And we can do them fairly quickly and locally. And it just requires local people to be involved in efforts like this. But we can, if there are excess nutrients going into an estuary, we can follow the example of the Medomic project and try to sleuth, pull our resources together, try to figure out what's going on and mitigate it. And it's the same with low pH. We can, these surveys give us the data we need to do further work. And a lot of people are utilizing citizen science data from Mid-Coast Maine, from MCOA and Coastal Rivers to build their own research and mitigation programs on. And I think that's all I have to say. There's so much more to do with the data. And, we'll be keeping you all posted as time goes on. And hopefully we'll be back out to a normal sampling year in 2021. And thank you so much for your interest. And it really is the volunteers. This is a grassroots effort, and it's really been encouraging to see the dedication and passion that the volunteers have shown for the estuaries that they care so much about.
Thank you so much, Kathleen. That was a wonderful overview of the information that we've got right now. So perfect for that. And yeah, I want to go off on what Kathleen was saying just for a moment and just say there is a lot we can do, both as an organization for coastal rivers. You know, we can take this data and use it for all sorts of things. It will help me when I'm talking to municipal governments and planning boards and things like that, to be able to say, well, yeah, we do see some nitrogen that we don't know what the source is yet, but we need to make sure that we're not increasing the amount of nitrogen that's being that's in the environment in our towns and immediately adjacent to the waterways, especially. So then it will also help me when you know, any of us are working on our own properties. It can help us make personal decisions about how the activities that we undertake and how big a buffer we might have on our shoreline if we are lucky enough to live along the river or along any waterway. And the better the buffer, the deeper the buffer, the more plant material and vegetation, the more it's going to stop runoff from entering the waterways, and the better it's going to control nitrogen overall. So there's a lot of things that we can do. There's information on our website about that. We at Coastal Rivers are working on a new resource that will come out to landowners in the area about all types of water protection that homeowners can take. Everything under the sun that we can think of, everything from, you know, do you have a lot of geese on your lawn, to do you you know, want to do something about the driveway runoff on your property, that sort of thing. So that will be forthcoming to residents in the next coming months. And so Haas's fingers waving. I'll come right back to you, Haas. Thank you. And so, you know, there's a lot we can do personally as an organization and within our communities as we are serving on local boards and participating in committees and so forth. So it's wonderful that you're able to come to this to get some of the information and be ambassadors into the community with this information. That's a great thing for you all. I will go through all the questions, but I guess I'll start with Haas's first, since he was just speaking to me. Go ahead.
Two pieces of data.
Yes.
Your station number 2, there are two things going on there. One, that's where boats from anywhere can dump their poop. The poop dumping is being done there. And second, it's in that area is the out pipe for the effluent for the Damariscotta town sewer system. They're both right in there. So
yes, Haas is exactly right. I do want to just clarify though that the boats aren't dumping the poop into the water; they're dumping the poop into the pump out station, or via the pump out station. Yeah, but that gets pumped out on land, as opposed to how it used to happen, which was that literally people were dumping from boats into the water, which is definitely not happening, at least to the same extent. So, but the point being that human waste is full of nutrients, and so there are points of entry. The sewage treatment sanitary district settles out the solids, but there's still nutrient material entering the waterways. So let me take and thank you, Haas, for waving your finger there. That was helpful. I could even see it on my screen. Now he's giving me the old. Let me just look at a couple of the other questions. There was a question from Jerry. Is it zooplankton rather than phytoplankton that actually is beneficial and feeds the critters in the river? And my answer to that, I guess, is depends a little bit on what types of critters you're talking about. Certainly phytoplankton, the plant-like things in the water that are microscopic and photosynthesizing, are one of the groups of small things feeding lots of other small things that feed larger things in the water. And zooplankton, some of which are very small and just as small as the phytoplankton, are also feeding small things that feed larger things in the estuary. So it does depend a little bit. And the reason why we talk a lot about phytoplankton is just because, well, there's several reasons, but one is that Kathleen was talking about how they produce oxygen. And so they perform many functions in the water column, partly providing oxygen to other creatures, partly providing food to bivalves and things like that. So I hope that clarifies that. Jerry, do you have anything to add to that, Kathleen?
Yeah, I just wanted to say, I think we wouldn't want to not mention the fact that we have millions of oysters in the upper Damariscotta River. And I meant to mention that and didn't. But when we have that excess phytoplankton growth, having those millions of oysters in the upper Damariscotta estuary that are filtering those phytoplankton out of the water are probably doing us a great favor, because they are, like I said, it's kind of like an incubator. You put the nitrogen in, the phytoplankton grow, the oysters are eating the phytoplankton. So those oysters, there's so many oysters being grown in the upper Damariscotta that really is an important part of that ecosystem, and we hadn't mentioned it.
Yeah, thank you. So Penny also asked, has there been any sampling of the Pemaquid River in recent years? And the answer is yes. There are volunteers who do a few readings on a regular monthly basis well, it depends on exactly what you call the Pemaquid. So the Pemaquid to me is the freshwater chain of ponds. And then that goes into the Johns embayment there. But so we're not doing any saltwater monitoring in where the Pemaquid comes into the ocean there, but it is our intent to start monitoring that region as well. And so and I was something we were planning on doing pre-COVID, and then it didn't happen this year just because we had a change of monitoring plan. But the freshwater is monitored, and it's something that the data is available on the Maine Lake Society page, and I can share that when I share the other information, like the recording of this. If anybody's interested in some of the freshwater data, that's available as well. It's hosted by another organization that we're part of a collaboration to do that monitoring. Great. I think that was the questions I see on the chat.
There was one about the locations being.
Oh, sorry, Anne. That's right. Anne asked about the locations in order to. Are they in order? Yes, they're in order. So thank you, Anne. They go from 1 being up in the Great Salt Bay to 7 being at the Darling Marine Center. Good. Dick and Emily, do you have anything to share with us any parting shots after all that work you did?
I actually have a question. I live in Waldoboro, and I obviously see the Potomac River on an incredibly regular basis. And it's, forgive me for saying this, but it's kind of a piddling little river. But why is it that the Potomac produces such a staggering amount of sediment compared to some of these other rivers?
I'll let Kathleen, do you want to talk about that? You certainly know more than I do about it.
I can theorize, but that's all I have is theories. But the geography of that steep valley that goes down into the Potomac, in the early days, I don't know if you've seen old photos, but there were no trees. That was all cut when it was settled and turned into pasture and agricultural fields, and a tremendous amount of sediment eroded down into the Potomac Valley, and it is very steep. I think that's one of the reasons why we have a lot of nutrient problems too and bacterial problems, because the town, everyone that lives in town is on that steep slope right in the village, and it all goes right into the head of the estuary. But a lot of that sediment was deposited due to massive erosion, I believe, when the trees were cut and the town was settled. And that fine sediment provides the perfect habitat for clams. And of course, we're still getting some erosion because it is a very steep topography. And that would be my theory.
Thank you.
Great. We'll come back to you, the Mackenzie's. I see there's a question now from Henry about, he asked, do any of these monitored phenomena contribute to the red tide episodes? Has red tide hazard increased in recent years? And worldwide red tides, or what we also call harmful algal blooms, which are caused by several different species of phytoplankton, they have increased worldwide. And they're a natural phenomena where you have this species of phytoplankton, and part of its regular metabolism, it creates biohazards, essentially. So there's a group of different compounds that have different effects on different people. For example, amnesic shellfish poisoning, or paralytic shellfish poisoning, or diuretic shellfish poisoning. And so these are all quite serious conditions, not only impacting humans, but some other animals as well, that consume the phytoplankton indirectly from bivalves mostly. And there are some other ways that red tides can impact fish, for example, and so forth too. But the question about nutrients or dissolved oxygen or any of these phenomena being contributing to red tides is that we don't see any direct impact currently, but it isn't something that how do I say this, that we have studied either. We haven't looked at any correlation, I would say, between for example, the nutrients and the red tide events that have happened. But we also know that the red tide events that we have had here are quite at least the ones that I can think of, are quite a bit larger than just a localized event. And the red tide events tend to come from down east or some other locations. Harpswell has a cyst bed for Alexandrium, for example. So the point being that they're not so localized as to probably be caused by what we are seeing by for example, the high nitrogen that we see by town. That's not, I wouldn't believe that would be connected to any of the red tide events around here, because they're larger than what we have seen in terms of impact from total nitrogen, for example. Kathleen, do you want to clarify any further on that?
Sure, I'll just comment, and I am not an expert on Alexandrium, but when Sarah showed that initial slide that showed the cold currents coming into the Gulf of Maine and kind of looping around counterclockwise and going along the down east coast and towards us and southern Maine, I believe there have been instances where, well, because the Gulf of Maine temperature is changing, it's changing the way those currents are passing. And the Gulf Stream is changing, the Labrador current's coming down from the Arctic, and more ice is melting. So that Labrador current, there's more fresh water coming in, and that comes around into the Gulf of Maine. A lot of things affect how that current, whether it hugs the coast or stays farther offshore. And like Sarah said, the Alexandrium forms cyst beds. And there's some thought that that the currents, when they're out in the Gulf of Maine, are picking up some of those cysts. And when that current comes close to the coast of Maine, and there are certain years that it is close, there are certain years where that current gets to the Penobscot, and because there's such a strong freshwater force coming out of the Penobscot, it turns back. There are sometimes when that current's so strong, it picks up the Penobscot and keeps coming towards us. And, there are some theories that the Alexandrium is being picked up and carried along the coast from those cyst beds in those instances. And this may, circling back to 2014, where we had that really low pH water, that may have had something to do with it. So we had a rainy season, lots of nutrients in the water, lots of rotting stuff on the bottom, and then we had this current that tends to carry deeper, colder ocean water, which tends to also have a lot of decaying. It's been sitting at a depth for a long time, so the pH is lowered, the oxygen levels are lower, and that came close to the coast. So we had the combination of a lot of nutrients coming from land, causing phytoplankton blooms settling to the bottom, depressing the pH and oxygen, and then that combined with this close pass of the coastal current in our area in the mid-coast. Of course, we don't know for sure, but that's one theory of what happened in 2014. And with the Alexandrium, that could have the pattern of that current could have something to do with the red tide.
Great. All right. Well, I think let's see if the Mackenzies have any parting shots about their experience going out very regularly this year in the river and doing this work for us.
Yes, I'd like to talk about the raging storms we endured most of the days we went out, and the broiling heat was just awful. We had a good time, and we're really happy that the data was useful, and that you pulled it all together.
That was
Very
Kathleen.
Nice presentation. Thank
That
you,
was Kathleen.
Yeah. Thank you. Yeah. It's so valuable to have. If we didn't have that year, and it's interesting too, because once we get to look at the data a little more, it'll be interesting to see if 2020 was different in some ways. I've taken a pretty cursory look at it, but 2020 was kind of an anomalous year in a lot of ways. And it would be interesting to see if there were any water quality effects that show up. So thank you very much for doing that.
Well,
you're welcome.
It's our pleasure.
Darren asked, will we be able to look at the graphs again? And Darren, since you're on staff, you can look at the graphs anytime you wish, but everybody will have a chance to access the information again if they wish. We'll send out the recording, and also I'll include the link for some of the freshwater data. And if anybody wants to look further at any of the information, just feel free to email us and we can provide that happily. So, all right. Well, you all were very great fortitude for listening to water quality data at what must be dinner time now. So thank you everybody for joining us, and we'll see you very soon, I'm sure. Take care.